Good morning to everyone. Last video we have discussed about the how we find the primary unknown values, and then based on the primary unknown values we can able to find the secondary unknown values and interpret the results. All those things we can see about the last videos, and how the physical model will be converted into an finite element model, and then depends upon the models how the output will be incorporated. All those things we can see about the previous video. In this video we can going to see about the derivation of one-dimensional linear elements. Here we are considering spring as one-dimensional element. Already previously we can discuss about in the assembly equations video. Here we are taking it as a single spring element. In this stiffness value will be in K, and then for a single spring they are having two nodes and one element. So that's why we are mentioning as an this is the element number, and then this is the node number. This is the single spring. They are having a two corner points. That will be a node 1 and node 2, and then the element number will be an 1. The stiffness value will be K, and then displacement of each nodes will be a node 1 for U1 and node 2 for U2. Correspondingly, the force value of node 1 F1 and node value of 2 is F2. We solve the derivation by using a potential energy method. Already we have discussed it in the previous videos. They are having a number of principles. Here we are using as a potential energy method. So potential energy equal to strain energy plus work done. Here the work done will be a negative, so that's why we are consideration minus. So strain energy minus work done. The strain energy formula is half K displacement square. So half into stiffness into displacement square, or we can use this as half force into displacement. So here we are considering displacement as U2 minus U1, because this is the final displacement, this is the initial displacement. So difference between these two values, that will be the deformation. So that's why we are consideration for a single element, the deformations will be an U2 minus U1. We will substitute this value in strain energy formula. We know half K phi square or U square. So half K instead of U we are applying as an U2 minus U1. So U2 minus U1 whole square. Then we will consideration the U2 minus U1 whole square will be take it as an A minus B whole square formula. So A square minus B square, sorry, A square plus B square minus 2AB. So for that the strain energy equal to half K U2 square plus U1 square minus U2 U1. Then we are going to find the work done. So work done means force into particular displacements. So based on the already we discussed, work done is based on the input force, how the output will be occurs. So that's why force into displacement. So node 1 we are consideration F1 U1 and node 2 F2 U2. So the total deformations, so total work done is F1 U1 plus F2 U2. We are applying the strain energy final equations, and work done will be in the equation number 1. So half K U2 square plus U1 square minus U2 U1 for a strain energy, and then minus work done will be an F1 U1 plus F2 U2. So finally we consideration potential energy equal to half K U1 square plus U2 square minus 2 U1 U2 minus F1 U1 plus F2 U2. So this is the final potential energy equations. Now we going to derive the equations based on the individual nodes. So for node 1 we want to find the equations by deriving the node 1 deformation. So that's why strain energy divided by deformation of U1. So dou phi by dou U1 equal to 0. For node 2, dou phi by dou U2 equal to 0, because the potential energy will be derivated by the node 2 deformation. So next we will see in the next video. Thank you.